Welcome back to our LeetCode series. Today we're solving the longest common subsequence problem, which is a classic dynamic programming question that frequently appears in coding interviews. Let's start by understanding what we need to do. We're given two strings, text1 and text2, and we need to find the length of their longest common subsequence. A subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. For example, if we have A, B, C, D, E and ace, the longest common subsequence is ace with length 3. The key insight here is that we don't need the characters to be consecutive, they just need to maintain their relative order. Let's work through a few examples to really understand this problem. Consider text1 equals A, B, C, D, E and text2 equals ace. We can see that if C and E appear in both strings in the same order, so our longest common subsequence is ace with length 3. Another example, if text1 is ABC and text2 is ABC, then the entire string ABC is the longest common subsequence with length 3. But if text1 is ABC and text2 is def, there's no common subsequence, so the answer is 0. The important thing to remember is that subsequences preserve the relative order of characters, but they don't have to be contiguous. Before jumping to the optimal solution, let's think about the brute force approach. We could generate all possible subsequences of both strings and then find the longest one that appears in both. However, this would be extremely inefficient. For a string of length n, there are 2 to the power of n possible subsequences. So for two strings of length m and n, we'd have 2 to the power of m times 2 to the power of n subsequences to check, which gives us exponential time complexity. This is clearly not feasible for larger inputs, which is why we need a more efficient approach using dynamic programming. Now let's solve this efficiently using dynamic programming. The key insight is that this problem has optimal substructure and overlapping subproblems. We can break down the problem as follows. If the current characters of both strings match, then the LCS length is 1 plus the LCS of the remaining parts of both strings. If they don't match, then the LCS is the maximum of either excluding the current character from the first string or excluding it from the second string. We'll use a 2D DP table where DP, I, J, represents the length of LCS for the first I characters of text 1 and first J characters of text 2. Let me show you how we build this table step by step. Let's implement our dynamic programming solution. First, we create a 2D array with dimensions m plus 1 by n plus 1, where m and n are the lengths of our input strings. We initialize the first row and column to 0 because an empty string has no common subsequence with any string. Then we iterate through each cell and apply our recurrence relation. If characters match, we add 1 to the diagonal value. If they don't match, we take the maximum of the cell above or to the left. The final answer will be in dp, m, n. This solution has O, m asterisk n, time complexity and O, m asterisk n, space complexity, which is much better than our brute force approach. Let's analyze the complexity of our solution. The time complexity is O, m times n, where m and n are the lengths of the two input strings. This is because we fill each cell of our DP table exactly once, and we have m plus 1 rows and n plus 1 columns. The space complexity is also O, m times n, for storing the DP table. However, we can optimize the space complexity to O, min is m n, by using only 2 rows instead of the entire table, since we only need the previous row to compute the current row. This optimization is useful when dealing with very long strings, but the basic solution is often sufficient for most interview scenarios.